Hi guys, and welcome to this virtual lecture course on Classical Mechanics and Relativity. I'm Dr. Andrew Mitchell, and in this lecture we'll be discussing the relativistic velocity addition formula. This will build upon the work we've been developing in the previous lectures on the foundations of special relativity, the Lorentz Transformations, the relativity of simultaneity, and length contraction and time dilation. So what we'll be discussing in this lecture is a very particular kind of thing. Imagine the following scenario. We have a person on the platform, and we have a train moving along the tracks, and we have a person on board the train. The person on board the train throws a ball with a particular velocity. But that velocity is relative to the person, and therefore relative to the train. How does the speed of the ball appear to the person in the station? So this is a classic kind of question within special relativity. It's about changing reference frames. We have the reference frame on board the train, we have the reference frame on the station. So according to Galileo and Newton, the person on the station simply says that the velocity that they observe is the velocity of the train plus the velocity of the ball. But this cannot be true in special relativity. We know this by considering the special case of light itself. If we shine light on board the train, the velocity of that light is not changed by the motion of the train. Light travels at the speed of light, and that's the end of the story. It doesn't matter what reference frame you're in. So what we see by going through the Lorentz transformations is, in fact, there's a modification to the velocity addition formula of Galileo and Newton, and we get a new formula due to Einstein. We'll be discussing some of the consequences of this. We'll see indeed that the speed of light is the same in all reference frames. We'll also see that nothing can go faster than the speed of light, according to this formulation. So we'll be discussing this and unpacking some of the ideas in this lecture. Also, we'll touch upon the hyperbolic geometry of space-time in this lecture, and we'll be developing that in future lectures as well. The idea here is that although the velocities aren't related in a linear fashion when you change reference frame, there is a quantity called the rapidity, which is basically the hyperbolic angle related to the velocity, which do add linearly. So we can view this as a kind of linear relationship between the velocities, but in hyperbolic geometry. So we'll be discussing all of this in the lecture. Let's get down to work.
In this lecture, we'll be discussing velocity addition within Einstein's special theory of relativity. To begin with, let's consider two inertial reference frames, let's call them S and S primed, which are in the standard configuration. What I mean by the standard configuration is that their axes are aligned. We see x, y, and z axes and x primed, y primed, and z primed axes in the same orientation. And at time t equals 0, the origins of these coordinate systems will coincide. At later times, however, the coordinate system S primed is moving along the positive x direction with a constant velocity v0. v0 is therefore the relative velocity between these two reference frames. Indeed, I can introduce the parameter beta, which is v0 over c, the speed of light, which I'll be using later. Now, the idea is that we consider a physical object in this space, not the coordinate systems themselves, but actually an object which is moving with some particular velocity in some arbitrary direction. Let's call it u vector. This is the velocity of this particle. In particular, this is the velocity of the particle in reference frame S. It's the velocity of the particle relative to our coordinate system S. Quite simply, our question is, how does the velocity of this object appear in reference frame S primed? I'll call this quantity u primed. It's the velocity of the particle as seen in reference frame S primed. As a warm-up, let's first consider the Galilean transformation. This is that x primed is equal to x minus v0 times t. This is the classical way of connecting the two reference frames S and S primed. This is not taking into account the effects of special relativity. Furthermore, we have the concept of a universal time within the Galilean transformation, meaning that t primed is simply equal to t independent of the reference frame, independent of the relative velocity v0 connecting our two reference frames. So what can we do with this information? Well, we can take the time derivative of this first expression here. How does that look? Well, I can write d by dt on both sides of the expression. I act with the operator d by dt on both sides. I have something like this. And of course, on the left-hand side, I have a velocity x primed dot. The dot just means d by dt. On the right-hand side, I have x dot minus v naught. V naught is, of course, a constant relative velocity. We're talking about inertial reference frames. Therefore, it has no time dependence of itself. The time dependence is completely captured here in the multiplication by the parameter t. So this is basically what we get, very straightforwardly, in Galilean relativity. We have a straightforward velocity addition formula. If I want to know the velocity in one reference frame, the primed reference frame, I take the velocity in the unprimed reference frame and just subtract off v naught. We can actually generalize this to a velocity in the unprimed reference frame u in some arbitrary direction and some arbitrary relative velocity between our reference frames, and then we simply obtain the vector addition generalization of the velocities, where u primed vector is equal to u vector minus v naught vector. We know, however, that this cannot be correct in special relativity. Why? Because consider light itself. Light moves with a constant speed, c, in all reference frames. So if we were to consider a beam of light in reference frame S, and we were to ask what speed it was moving as seen from an observer in S primed, according to Galilean relativity, the speed would be changed by the relative velocity between S and S primed. But this is not the case in special relativity. We know that light travels with a constant speed in all reference frames. So this formula will have to be modified. And although this seems like a very natural formula, which applies at non-relativistic speeds, and here I mean both that the relative velocity v naught connecting our two reference frames, as well as the velocity of the object u, are small compared with the speed of light, then we'd expect this formula to be satisfied. But when we go to relativistic situations, either when the relative velocity between the reference frames is itself large, or when the objects we're talking about are moving very quickly, then we'll have to refine this formula according to special relativity. So how do we do that? Well, of course, we switched to using the Lorentz transformation rather than the Galilean transformation. So here I've written out the Lorentz transformations for this situation where we have a relative velocity of our two coordinate systems, s and s primed, along the x-axis, parameterized by this relative velocity in the units of the speed of light, which is called beta. We also have this parameter gamma, which is 1 over the square root of 1 minus beta squared, which is called the Lorentz factor, and this controls the strength of relativistic effects, as we'll see. So in this Lorentz transformation, we have that the time, ct primed, is now no longer universal. It's related to ct in this way, also to the spatial coordinate x. X primed is also depending on x and ct. Y primed is equal to y, z primed is equal to z. This means that the y and z coordinates of the primed reference frame are equal to their unprimed reference frame counterparts because the relative velocity is not along the y or z directions, but only along the x direction. So we see that space and time only get scrambled up according to these two equations in the direction of the relative velocity. Okay, so how do we work out the velocity addition formula? Well, you might think that we just simply do what we did before and take the time derivative of the expressions here to find the velocities. But we have to be a little more careful, because what do we mean by the time derivative? In particular, which time are we talking about? Are we talking about the time t or the time t primed? They mean different things in the different reference frames, so we have to be more careful. In the unprimed reference frame S, we'll say that a velocity component along the x direction, called ux of a particular object, is simply dx by dt, where x and t are both in the unprimed reference frame. Likewise, the velocity component along the y direction, and along the z direction, uy and uz, are respectively related to the derivatives dy by dt and dz by dt. So how does this look in the primed reference frame? Well, then we have ux primed, uy primed, and uz primed as simply the derivatives of the spatial coordinates with respect to the time coordinate, but this has to be done in the primed reference frame. So for example, ux primed now has the meaning dx primed by dt primed. So let's now use these definitions to derive expressions for the velocity addition formula within special relativity. We'll start with an expression for ux primed. This is the velocity of an object along the x direction in the primed reference frame. By definition, that means dx primed by dt primed. But let's now use chain rule to express this as dx primed by dt divided by dt primed by dt. By the way, this is an alternative form of the chain rule. This is entirely equivalent in this case to dx primed by dt multiplied by dt primed. Those are equivalent expressions in this case. Now, we can easily calculate dx primed by dt because we have an expression for x primed in terms of x and t. So let's go ahead and compute that expression. We'll obtain gamma multiplied by dx by dt minus beta c dt by dt. So clearly this object dx by dt, by definition, is simply the velocity of the object along the x direction in the unprimed reference frame. So this object is simply ux. dt by dt is of course just equal to 1. And beta times c is actually just the relative velocity v0. In this expression, you'll notice that I have beta, c, and gamma. They are all constants. Beta is simply the relative velocity in units of the speed of light between the two reference frames, and the relative velocity is a constant. Gamma is simply 1 over the square root of 1 minus beta squared. That's also a constant. Okay, so all of this expression has to now be divided by this second factor, which is dt primed by dt. We have an expression for t primed in terms of t and x, so we can again just go ahead and compute that. Dividing by c on both sides and then taking the time derivative with respect to t rather than t primed, we obtain gamma over c times c dt by dt, which is 1, minus beta dx by dt, which is, of course, ux again. Rearranging and simplifying this expression, we finally obtain this final form. It's ux primed is equal to ux minus v0 on the top. That's what we got from the Galilean transformation. But now this is divided by this factor, 1 minus v0 ux over c squared. This is an important expression. It's Einstein's velocity addition formula. Here, it's important to remember that the velocity of the object, ux, in the unprimed reference frame is in the same direction as the relative velocity v0 between the reference frames. That's the situation where we have ux minus v0 on the top, just like in the Galilean transformation. In the moving reference frame, the velocity of the object appears to be somewhat reduced. However, in special relativity, it's reduced by a smaller amount than it would be in Galilean relativity. That's because downstairs here we have this factor 1 minus v0 ux over c squared, and since v0 and ux are in the same direction, this whole factor is a number that's less than 1. Therefore, there is a reduction of the velocity, an apparent reduction, but it's not as strong a reduction as one would obtain in Galilean relativity. So let's take this formula that we've just derived for relativistic velocity addition and consider two important limits. The first one will be what happens when we consider light itself. Let's consider a situation where ux is actually the speed of light, c. In that case, we have that ux primed, the speed of light in the primed reference frame, would be equal to c minus v naught over 1 minus, and if ux is equal to c, well, we have one factor of the c cancels upstairs and downstairs, and we have v naught over c. I can multiply this expression top and bottom by a factor of c, and we would obtain c into c minus v naught on the top, and on the bottom we'd have c minus v naught. C minus v naught cancels top and bottom, and we obtain the speed of light c. This is, of course, extremely important because it tells us that indeed, according to relativistic velocity addition, the speed of light is the same in all reference frames. This is important because irrespective of the relative velocity connecting our two reference frames, v naught, this factor just cancels out, and we obtain the speed of light as something which is constant in all reference frames. So this result confirms the fundamental postulate that we actually started out with. The second important limit is the non-relativistic limit. So let's consider the case when the relative velocity v naught is much, much less than the speed of light c. This is the thing that we'd normally consider to be the non-relativistic limit. How do we deal with this limit? Well, we introduce the small parameter beta, which as usual is v naught over c. But since ux is less than or equal to the speed of light, then we can say that ux over c is less than or equal to 1. Overall, then, we have the factor ux v naught over c squared that actually appears in our velocity addition formula is something, therefore, that is much, much less than 1. So this holds in the limit v naught is much, much less than c, actually for any permissible ux less than or equal to c. Remember, v naught here is the relative velocity between our two reference frames, while ux is actually the x component of the velocity of some physical object. It could be light, it could be something that's really moving along like a spaceship. Ux is therefore at most the speed of light, c. Why is this important? Because here we have a small parameter, ux v naught over c squared. This object is definitely much, much less than 1 in this limit that we're considering. And that means we can analyze this velocity addition formula. We can do that using a Taylor series, and we'll obtain that ux primed is equal to ux minus v naught, that's the factor on the top, and then we can expand the 1 minus something small to the minus 1 as 1 plus the something small. The something small in this case is of course ux v naught over c squared. And then we have higher order terms in the Taylor series expansion, which are ever smaller and smaller in magnitude, and therefore I'll neglect. Okay, so normally what you might expect here is that we can just cross out this small term here, and then we'd be left with 1 times this prefactor, and that would of course be the Galilean transformation of the velocities. But this is actually not quite correct. As we just saw, the limit where ux is something large compared with the speed of light, ux tends to c, is actually not described by the Galilean transformation. We know that the speed of light is the same in all reference frames. So this seems to indicate that when ux is large compared with the speed of light, we actually can't throw away this term. So let's analyze this expression and see why that's the case. If I just multiply this out, then I get the following terms. I get 1 times ux minus v naught. This is the usual piece from the Galilean transformation. And then we get two cross terms involving this small parameter times these two things, and I've written them out here in this form. Then we have higher order terms here that I'm neglecting. Okay, let's have a look at these other two pieces. Now, very obviously, this piece is very small and can be sent to 0 and neglected. Why is that? because here we have v0 over c squared times ux. So this term is something that we can neglect because v0 over c, otherwise known as beta, is much, much less than 1. So v0 over c squared is very, very small, and we can throw it away, even when we multiply it by a factor ux. However, that same argument does not apply for this piece. So here I've written it as ux over c squared times v0, but I've not included in my definition of the non-relativistic limit any restriction on the size of ux. So ux over c could actually be a number of order 1. Of course, ux cannot be greater than the speed of light, but this could be some appreciable fraction of the speed of light. In an extreme limit, when we're considering light itself, as in the first case, ux could be equal to the speed of light, and then we'd have literally here the number 1, and then we'd have a correction of order v, which is large. So the punchline here is from the Taylor series, when we consider this naive non-relativistic limit, v0 much, much less than c, we actually still get a potential large correction here of order v0, and that changes the usual Galilean transformation. So it appears that we do not recover necessarily the Galilean transformation when we consider the non-relativistic limit v0 over c. This forces us to reconsider what we mean by the non-relativistic limit. To have both of these two terms vanish, leaving us just with the Galilean transformation, we actually, as you can see quite clearly from this analysis, need both ux over c to be small and v0 over c to be small. So, in terms of velocity addition, the Galilean transformation is recovered when both ux and v0 are small compared to the speed of light. This means that the relative velocity between the two reference frames that we're considering has to be small compared with the speed of light, but also the speed of the objects that we're considering has to be small compared with the speed of light. We need both of these two terms to vanish to recover the Galilean transformation. In particular, as we already saw in the first limit, if we're considering light itself, then the Galilean transformation is no good, even when we consider a modest relative velocity between our reference frames. So let's start again. Let's consider a more sophisticated version of the non-relativistic limit, in which v0 is much, much less than c, and also ux is much, much less than c. In this case, we find the recovery of the familiar Galilean transformation with corrections which are only very, very small. We see corrections of order ux over c times v0 over c, and in this limit that we're considering, this is a very, very small quantity. So indeed, we obtain something to high accuracy in this limit that is recovering the classical Galilean transformation of velocities. So if by non-relativistic limit we mean the limit in which we recover classical Galilean or Newtonian physics, then indeed we need to consider both v0 much less than c as well as ux much less than c. So let's now consider the example of a ball thrown on board a moving train. So in my very badly drawn cartoon here, I have someone standing on the station, and he's at rest. We have in black here the station rest frame. In the station rest frame, we see the train moving with a velocity v. That's depicted here, that's what's in blue. A person on board the train then throws a ball with the velocity u relative to the train. So someone on board the train throws a ball, they throw it with velocity u, but that's with respect to the train. The question is, what is the velocity of the ball to someone in the station rest frame? Let's call that velocity w. So to recap, in black we have the station rest frame. We want to know the velocity of the ball in the station rest frame, that's w. The train is moving along at a velocity v relative to the station, that's drawn in blue. In red, we see the ball moving with a velocity u relative to the train. So the standard result coming from the Galilean transformation, which is just simply velocity addition, would be that w is equal to the velocity of the train v plus the velocity of the ball with respect to the train, which is u. Now, we know this can't be the result in special relativity, because if the train was moving very, very quickly, and we threw the ball very, very quickly, then it would be possible for this w here to exceed the speed of light. So what is the correct result from the Lorentz transformation? In our previous derivation, we had the situation where we had a velocity measured with respect to the rest frame, and then we wanted to know how that velocity looked in the moving frame. Here it's slightly different, because we have a relative velocity of the ball with respect to the moving train, and we want to know how it looks in the rest frame. So actually we want the inverse transformation. So let's switch now to the train rest frame. The second illustration here is in the train rest frame. So the thing that's in blue here, the train, is at rest. We have the velocity of the ball in red with respect to the train, which is at rest. So this is the correct velocity u here in the train rest frame. But the station looks to be moving in the opposite direction now, with a velocity of minus v. So this is actually the appropriate setup in which our derivation on the previous slide holds. We consider the rest frame of a given situation with an object with a velocity u measured in that rest frame, and then we want to switch to the moving frame, which in this case is the frame of reference of the station. So we can now apply the formula that we derived on the previous slide. That gives us the following. We see that w, the speed of the ball as measured in now the moving frame, which is the station frame, is the speed of the ball in the rest frame, meaning the train frame, minus the relative velocity, but the relative velocity is now minus v. And that's all divided by 1 minus u times minus v over c squared. The reason for these minus v's in here is now the relative velocity between the train and the station is minus v when considering the rest frame of the train. And therefore it gives us u plus v over 1 plus uv over c squared. So this is actually the inverse transformation for the velocity addition formula. Actually, it's completely trivially related. We just swap v for minus v. To avoid getting confused by this, there's a simple rule of thumb. Think about the Galilean transformation, where our regular intuition holds. So there we know very clearly, and for obvious reasons, that w should be equal to v plus u. We can see from the diagram the speed of the ball relative to the train is u, the speed of the train relative to the station is v, we just add them up in the classical world. So this gives us the intuition for the sign. It's v plus u in this case. In the relativistic world, of course, we use the relativistic velocity addition formula, and we again just pick the signs according to our intuition from the classical world. So it's u plus v in this case. That tells us that the velocity is has this plus sign, and therefore downstairs as well we also have the plus sign. So just be a bit careful with this when you're doing problems yourself. It's either a minus on the top and a minus on the bottom, or it's a plus on the top and it's a plus on the bottom, depending on whether you're using the forward transformation or the backward transformation. The intuition about which sign comes from the Galilean transformation. That's the easiest way to do it. In any event, w has a specific meaning, and that's the thing that we wanted to know. It's the velocity of the ball relative to the station. So here's the summary. From the Lorentz transformation, we find that w is v plus u over 1 plus uv over c squared. Let's now analyse this formula to see what happens as we increase the velocities so that relativistic effects become important. In particular, I want to test the idea that nothing can go faster than the speed of light. According to the Galilean transformation, it would be very easy to obtain velocities that were above the speed of light. Consider the following. Imagine that I had a train moving at 3/4 of the speed of light, and then a person on board the train threw a ball also at 3/4 the speed of light. According to the Galilean transformation, I simply add these up, and from the station rest frame, I would see a ball moving at 1.5 times the speed of light. So let's check that that's actually not possible within a Lorentz transformation, and that the ball can never be travelling faster than the speed of light in any frame. First of all, let's suppose that we have a fairly modest speed. This is where I'll assume that the ball is thrown with a velocity of 1% of the speed of light, and also the train is moving at 1% the speed of light. This translates to something like 3 times 10 to the 6 meters per second. So when I said this is a modest speed, of course this is a fantastically high speed, it's just that it's still only 1% of the speed of light. So what happens in this case? What is the speed w of the ball in the station rest frame? Well, let's just plug the numbers in to our Lorentz Transformation velocity addition formula if both u and v are 0.01 c. In that case, w is 0.01 c plus 0.01 c divided by 1 plus 0.01 c squared over c squared. So there's some cancellation going on here, and in fact you can tidy it all up, and we're going to obtain something that's basically 0.02 c. Where did I get that from? Well, we have 0.02 c from the top, and on the bottom we have something that's basically 10 to the minus 4. So we have the factors of c cancel here. We have c times c over c squared, and we're just left with 0.01 times 0.01. That's a correction on the bottom to the 1 of order 10 to the minus 4, and I've just neglected that. So w is not equal to 0.02 c, it's approximately equal to, let me change this sign to an approximate sign. So in this case, we see something that is basically Newtonian. It's the results that we'd obtain if we just naively went ahead and used the Galilean transformation, where we just sum up u and v. So you see that even when we're going rather quickly, at a speed of 3 million meters per second, because it's still only 1% of the speed of light, the Galilean transformation is actually working rather well in this case. Of course, if you had sensitive machinery, I'm sure you could measure the deviation, which is 0.1%. That's still something you could probably measure. Okay, so let's now consider the much more interesting case when we're going at very, very high speeds relative to the speed of light. Let's consider now 90% of the speed of light. U and v are both 0.9 c. So of course this would give, according to Newton and Galileo, w of 1.8 c, which is of course greater than the speed of light. So what do we get according to special relativity? Well, we use the same formula as before, but this time we use 0.9 c. We just plug those numbers in and see what we get. So on the top, we get 1.8 c, and on the bottom, we actually get 1.81 c. Why is that? Because, again, these factors of c, top and bottom here cancel, so we get 0.9 times 0.9. That actually gives me 0.81. I add it to the 1, and I obtain this. So this is rather interesting, because what it tells us is that the bottom is very slightly larger than the top, and therefore this is something that is almost the speed of light, but still less than the speed of light. So we see a very big discrepancy here between the Galilean transformation and the Lorentz transformation for the velocities. According to the Galilean transformation in classical Newtonian physics, we'd see a velocity w that exceeded the speed of light, whereas with the Lorentz transformation, we can't quite get there. In fact, if you were to analyse this equation, you would see that the bottom will always be greater than or equal to the top. Only in the limiting case, when either u or v are equal to the speed of light, do we find that w is equal to the speed of light. Anything less than that for u and v would give us a w that is less than the speed of light. So indeed, if we start with an object that's moving slower than the speed of light, then it's impossible for in any other reference frame for that to appear to be moving faster than the speed of light. There's a fascinating experiment that illustrates the effects of relativistic velocity addition, which is to measure the speed of light in flowing water. This experiment is called the Fizzo Experiment and was actually performed in 1851. This is very early. It's earlier, way earlier, than Einstein's special relativity. As we'll see, there's an interesting result from this experiment that could not be understood in terms of the physics at the time. It took Einstein to come along and actually understand the results of this experiment. This is a little illustration from the time of Fizzo's experiment. It involves these long glass tubes which are connected to a pump and this water cylinder here. So the water is just cycling around and flowing in the system. Then Fizzo shone some light down these tubes, and in a very clever way, he was able to measure the speed of the light in the flowing water. That was actually done spectroscopically, so he considered basically this setup. This is a simplified version of what he did, but basically you shine some light, it hits this beam splitter and separates the light into two coherent beams. One of them is propagating in the opposite direction to the flowing water. The other one, which takes this red path, is flowing in the same direction as the flowing water. When these two beams recombine, if there is a difference in the speed of light due to the travelling in one or other of the arms, then you will see an interference pattern in the detector. The observed interference pattern is actually enough to work out the speed of the light in the flowing water. So this is a really ingenious experiment performed quite early on in 1851 by Fizzo. So what do we expect the velocity of light to be in flowing water according to special relativity? Well, first of all, we know that the speed of light in a vacuum is c, whereas the speed of light in water, and here I just mean stationary water, the water is not flowing, it's just still, is c over n, where n is the refractive index of the water. And since n is greater than 1, it means that the speed of light in still water is less than the speed of light in the vacuum. Now suppose that we have water flowing with a velocity v in the laboratory frame. The question is, what is the speed of light in the flowing water in the laboratory frame? Let's call that u. So according to the Galilean Transformation, the usual classical physics of Newton and Galileo, we would obtain that the speed of light in the flowing water, u, is simply equal to the speed of light in the static water, which is c over n, plus the speed of the water itself, which is v. What about the velocity addition formula following from the Lorentz transformation? In that case, we obtain that u is equal to c over n plus v, as before, but then it gets corrected by this factor on the bottom, 1 plus c over n times v over c squared. This is just a direct application of the velocity addition formula that I wrote down on the previous slides. Okay, so let's analyse this expression. The first thing I can do is cancel one factor of the speed of light c in this expression here, because there's a c on the top and then there's a c squared downstairs. And when I do that, I get 1 plus v over cn. Now, we're assuming that the velocity of the water, v, is much, much less than the speed of light, c. That's fairly reasonable, and so v over cn is a small parameter. Therefore, we can use Taylor series to expand the denominator here. Then I obtain this expression. I have c over n plus v, which was the stuff on the top, and then I expanded the bottom, 1 minus v over cn, plus terms of order v over cn squared. If v over c is small, which we're supposing it is, then v over c squared is going to be very small, and so I can neglect this piece. So this is very similar to the calculation I did on the previous slide. Let's just expand out this piece now. This whole thing will be approximately c over n plus v. This piece is actually the same as what we would get from the usual Galilean transformation, but then we actually get some extra terms. By multiplying c over n by minus v over cn, we get this term, and by multiplying v by minus v over cn, we get this term. Now, this last term will, of course, be very small, because v over c is very small, and v itself is not something that's very large, so we can actually neglect that piece to leading order. But something rather interesting happens in this remaining piece here, because the speed of light c actually cancels top and bottom in this expression. And that leaves us with something that is not very small. This term is actually appreciable and can be measured in the experiment. We get a term that's minus v over n squared. Remember, v is the velocity of the water, and n is simply the refractive index of the water. So this is the result we'd expect from the Lorentz transformation. We don't just get simply the Galilean result, where we add up the velocities, but we get a correction to that, and that correction is actually not small. It's equal to v over n squared. That is something that could, in principle, be measured, and indeed, this exact factor was precisely measured in the experiment in 1851 by Fizzo. I think this is a truly remarkable result. It actually presaged the results of special relativity. The people working at the time had no idea about this calculation, and yet they actually measured this correction. There was no explanation for that at the time. Had people really examined the results of this experiment carefully, it could have led to the discovery of special relativity, I guess like 50 years or so early, because this was really the first sign that there was something up with classical mechanics and that a refinement had to be introduced. That refinement, of course, is special relativity, and we see that this correction here that was observed experimentally comes out very naturally from the Lorentz transformations. There are some other fascinating consequences of relativistic velocity addition that we see in the field of astrophysics. In particular, we see the relativistic Doppler effect, and we also see the aberration of light, as it's known. These are both effects coming from the relativistic velocity addition formula, and we'll actually be discussing those in the relativistic optics lecture yet to come. So far, we've considered the relativistic velocity addition formula for a velocity in the x direction when there's a relative velocity between our two reference frames that's also in the x direction. This could be called a longitudinal velocity addition. In classical Galilean relativity, the relative motion along the x direction does not affect the y and z directions. However, we'll see, in fact, as a correction in the relativistic world, and I'll refer to this as a transverse velocity addition. In particular, I'll ask, what does uy primed look like, the velocity component in the y direction, in the primed reference frame? By definition, this is dy primed by dt primed. Now, when we look at the Lorentz transformation that I've drawn here in red, we see that y primed is equal to y, and so you might be forgiven for thinking that there's no correction. But of course, t primed is actually transformed as well, and therefore we will see a correction, a transverse correction to the velocity addition formula. So how does this work? Well, we can write dy primed by dt primed via the chain rule as dy primed by dt divided by dt primed by dt. Now the first factor, dy primed by dt, is actually simply equal to dy by dt, otherwise known as uy. This follows from the definition of y primed being equal to y, and dy by dt being uy as per the definition. The factor dt primed by dt is something that we calculated previously, and it simply follows as gamma over c times dt by dt, which is of course just equal to 1, minus beta dx by dt, which is of course just equal to ux by definition. So let's collect up all those terms and tidy things up a bit, and then we'll obtain our final result for the transverse velocity addition uy primed in terms of velocities in the unprimed frame. And this is the result. We see that uy primed is equal to uy divided by gamma into 1 minus ux v naught over c squared. So if this was the Galilean transformation, uy primed would simply be equal to uy. Here we see a correction, and it actually involves the velocity along the x direction. as well as the gamma factor. Exactly the same calculation follows for the velocity component along the z direction. We see that uz primed is just equal to uz divided by this same factor. So, even though we only have a relative velocity along the x direction connecting our inertial reference frames s and s primed, that's a Lorentz boost along x, the velocities uy primed and uz primed in the prime frame of reference are actually affected by the relative motion along the x direction. This is because of the time dilation effect. It's coming from this factor dt primed by dt in both cases. This would be totally unexpected from the perspective of the Galilean transformation. So overall, we have a velocity u in the original rest frame s, which has components x, y, and z. When we transform to the moving frame s primed, we have new velocity components ux primed, uy primed, and uz primed, and each of these gets affected by the relative motion, even though that's only in the x direction. The last topic that I want to talk about in this lecture is the hyperbolic geometry of spacetime and the role played by so-called rapidities. I'll develop this in much greater detail in the coming lectures. I just want to touch upon it here, but we'll already learn something interesting. If we look at the Galilean transformation of velocities, then we see simply a linear relationship. That is, that ux primed is equal to ux minus v naught, where ux is the velocity in reference frame s, and v naught is the relative velocity between s and s primed. When we move to special relativity and consider the Lorentz transformation of velocities, we see a non-linear relationship between the velocities here. As we'll see, this can be considered as a difference in the geometry of underlying spacetime. Now, in classical physics, the geometry of three-dimensional space is simply flat Euclidean space. When we generalize to four-dimensional space-time, we'll see that it's no longer a Euclidean geometry. In fact, it has a hyperbolic geometry. If we consider an underlying hyperbolic geometry of spacetime, then we'll see that the velocity addition is actually again a linear relationship. Let me explain what I mean by this. First of all, notice that the velocities ux, v naught, and ux primed are all numbers that can range between plus or minus c. Therefore, the parameters ux over c, v naught over c, and ux primed over c range between -1 and +1 in each case. Therefore, we can actually make a bijective map between these parameters and the hyperbolic tangent of some parameter phi u, phi v, and phi u primed. These phi's are referred to as rapidities. They are basically the hyperbolic angle. So what? Why are we interested in this? Well, we can write the Lorentz transformation of the velocities, as I've written here, in terms of these rapidities. First of all, let's divide by c on both sides of this expression, and tidy it up a bit. Then I obtain this expression, and I've written everything now in terms of these dimensionless ratios ux primed over c, ux over c, and v naught over c. Now I can substitute in these expressions in terms of the rapidities. Then we obtain this expression, that tanh of phi u primed is equal to tanh of phi u minus tanh of phi v over 1 minus tanh phi u times tanh phi v. This expression might look very horrible and of no use to us, but actually this is one of the hyperbolic trigonometric identities. This object on the right-hand side here is actually one of the compound angle formulas for tanh. You can look it up, and what you'll find is that this expression here is precisely equal to the hyperbolic tangent of phi u minus phi v. So on the left-hand side, we see the hyperbolic tangent of phi u primed, and on the right-hand side, we see the hyperbolic tangent of phi u minus phi v. So let's now just take the inverse tanh function on both sides of this equation. We therefore find that phi u primed is simply equal to phi u minus phi v. This is exactly analogous to the original Galilean transformation of velocities. Ux primed is equal to ux minus v naught. So what we see is that when we go to special relativity, we see the same kind of linear relationship, but in terms of the rapidities rather than the velocities. This is actually the first hint that what we are dealing with in four-dimensional spacetime is actually a hyperbolic geometry, and we'll be returning to this in much more detail in the coming lectures. For the purposes of this lecture, it's important to understand simply that for the Lorentz transformations of special relativity, we have a velocity addition formula that actually involves these rapidities. In terms of the rapidities, we have something that looks very much like the usual Galilean transformation of the velocities. The rapidities themselves are actually the inverse hyperbolic tangent of the velocities divided by the speed of light. We'll be applying these concepts in the coming lectures.